All right, good afternoon, everyone. Today we'll spend some more time on analysis of circuits using series parallel equivalents. Then we'll see how we can apply voltage division, current division for the same circuits. The point is, I want students to get comfortable in trying to solve for circuits using a variety of different methods. Okay, so everything that you learn in here in 113, especially like Thevenin theorem, Norton theorem, later on in this course, you will apply again and again throughout, in multiple, several courses down the line. Okay. So at that point, when you're trying to analyze a circuit, professors who are teaching you something about semiconductor devices will quickly say, okay, we are taking the Thevenin equivalent circuit of this, and the current's being divided here. So it's half, 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 half. So every student needs to be able to understand what is actually going on in terms of circuit analysis, because in higher level classes, they are not going to recap this. So it needs to become like second nature, for electrical engineers. So let's take a look at example number 2, right? Now, the circuit at first glance seems rather straightforward, right? We have a 5-6 resistor circuit, all connected either in series or in parallel. And then the first step for this would be to start to solve for Req, apply Ohm's law, and obtain the voltage across the current source. But we can also apply voltage division, current division as part of our analysis. Okay, so this is one of those circuits that I particularly like because it can encompass all three techniques, right? You can also apply KVL, KCL to solve for currents and voltages at different nodes. Okay, so let's begin. Take your calculators out and we'll go along solving. So what we want to do is reduce the circuit to one single Req resistance as seen from the perspective of the current source. Remember, in the previous circuit, we solve for the current. In this circuit, because it's a current source, we are going to solve for the voltage. This one also is a current source. Okay, then both cases are the same. If it's a voltage source, we solve for the current. If it's a current source, we solve for the voltage. So we want to find Req, 2K and 3K, series or parallel. So if we want to find Req, we always start at the farthest end away from our source, and then we start reducing the circuit step by step until we reach our source. Okay. There is one more technique I wanted to show students. So, all right, let's do it this way. Sometimes there are tricky circuits. Sometimes there are circuits where you cannot reduce it using normal methods. You cannot find Req simply by combining resistors in series and parallel. Okay. Sometimes there are circuits that are reducible, but it's not as straightforward. So for those, there is a technique that I developed. Now, I don't know if it's just me, but I have not come across any book or any other place that uses the same technique. So if we take a look at this example, right? We have 3 series resistors on the left, 2 parallel, and 1 on the right. So if I want to find Req for this example 1, this is the previous one from the last slide. Okay. So we had 3 resistors here. We have the current source here. This one was slightly easier because it's 2 parallel and 3 series on the left. But the way to find Req for most circuits can be done like this. You draw 2 horizontal lines, spaced a little bit apart. This represents terminal A, this represents B. And the objective of the goal is to redraw the circuit traveling from point A to point B. Okay, traveling from point A to point B. And the method to do so is you want to draw all the resistors in a vertical direction. So you get parallel pathways. So if I start at A and I call this R1, R2, actually, no, what did I call it? Let's stick with the same convention. R1, R2, 3, 4, 5, and 6 at the bottom. Okay. So this was R1, R2, R3, R4, R5, and R6. Okay. So now, if I start at A, how many paths can I take to go to B? There is one on the left where I can start from A and I can go from R2. R2 is connected to R1 and R1 is connected to R6, which leads me to B. This one's obviously straightforward because it's evident that they are all in series. But does this logic make sense? We are going from point A to point B because between A and B is where our source was connected. This is where we are measuring the total equivalent resistance. Okay, so A and B. How about the right? We'll draw it a little bit away. We have R3, right? We're starting to go around circuit. R3 is connected to two resistors. So I'm going to split. I'm going to draw out those resistors. So this would become R4. This would become R5. And then both those resistors are connected together. And that is connected to node B. So simply going to connect these together and connect that to node B. Thus, I have my REQ. I can measure REQ between A and B. Now, all resistors will either be in parallel or they will be in series. So now I have two independent circuit branches. This also allows me to see if it's a voltage source, the same voltage is applied to both branches or all branches in the circuit. If it's a current source, then I can see that current is being divided. But the voltage between the two nodes will remain the same. So this technique will work on most circuits. However, there are still some circuits where you cannot reduce it to 0. But this will work for most circuits. All right, let's take a pause. Let me know if you have any questions. Okay. No questions? Okay. All right, let's go to example 2. So this one, again, start at the farthest end and move towards your source. At the farthest end, let me name this R1, R2, R3, R4, R5, R6. At the farthest end, we have 2K and 3K. They are both in series. So I can reduce it step by step. And let's see. Some better drawing. Okay. And I'm going to call this R7. R7 is R5 plus R6, which would be 5 kilo ohm, right? 5 kilo ohm. And then we see R7 would be in parallel with R4. So let's call that R8. And somebody perform the calculation. Well, actually, everybody perform the calculation. And let me know what the answers are. Yes. 4K. Thank you. 4K. 4K. Anyone from the left or my left? Anyone at the back have a different number? Right. 4 kilo ohm. 20 times 5 divided by 25. So if you have two resistors, that was one of the other things. Let me note it down when we do resistors in parallel. Oh, we just did voltage division, never derived. Voltage division, series resistors. All right, so if you have resistors in parallel, I believe I thought I had it somewhere. Oh yeah, here. You have n resistors in parallel, all with the same value R. Req is R over N. If you have two resistors in parallel, let me note it down here. The Req is the product of the two divided by the sum of the two. So if you have R1 in parallel with R2, then Req is the product of R1 and R2 divided by the sum of R1 and R2. So we had 20 and 5. 20 times 5 is 100. 100 divided by 25, 4. And you can do that equation. 1 over R1 plus 1 over R2 gives you R1 plus R2 divided by R1, R2, reciprocal, product of the two divided by the sum of the two. It's a quick and easy shortcut to remember. Of course, with modern calculators, everything is easy. Anyway, so 4 kilo ohms is now in series with R3. Let's call that R9. And so R9 is R3 plus R8, which would be 4 plus 5, so 9 kilo ohms. This is R2, this is R1. And then final Req. Someone perform this calculation. Again, not someone, sorry, everyone perform this calculation. REQ is R1 in parallel with R2 in parallel with R9. Therefore, our REQ is, what is our REQ? 6K in parallel with 24K in parallel with 9 kilo ohms. 5, and 20 gives me 4. Oh, it's not 9, sorry, it's 8. Nobody is paying attention. Or maybe you did, but you're afraid to speak up. It's fine. You're not going to hurt my feelings. If I make an error, please point it out. Okay. That's not 9K. It's 8K. All right. So 6, 24, and 8. What do we have? Three, 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 once, twice, and thrice. Oh, 3K. REQ is 3 kilo ohms. So if REQ is 3 kilo ohms, now let's find the voltage. Let's call it VS. And VS, because it's a parallel circuit, sorry, not there, just there, all the way up to here. I'm going to call this as IS, current source IS, voltage VS. Apply Ohm's law. What do we get? So IS VS 50 milliamps. VS is equal to IS times REQ. Therefore, VS is equal to 50 into 10 raised to minus 3 into REQ, which is 3000. So obviously 10 raised to minus 3 and 1000 cancel out. 3 times 50 is 150 volts. So 3000, 3K, IS is 50 milliamps, and it's 3000, 3 times 50, 150. Do you all agree, or did I get it wrong? 10 points to me. All right. Any questions before we move on to the analysis? So far, so good. Very good. Okay. All right. Then let's observe the circuit. We have VS, right? Now our job is to expand the circuit one step at a time. Since we have the current IS and we have the voltage, let's look at both. If you take a look at IS, it goes down here, but because this is a parallel circuit, as soon as we hit the first node, some of it's going to go down here, some of it's going to go down here, some of it's going to go there, there, there. Splits, right? Splits at every step. So we want to find the point where either one of the quantities is going to remain constant. Current at the first node is going to split and change. So we can't obviously use that to find a answer for the resistor voltage and current, right? And we cannot directly apply current division yet, not unless all of them are in parallel. So we can apply current division at this step. Yeah, that's what I said. There are multiple possibilities depending on what quantity we need to find. Okay, we could apply current division. So current division, let me read the full form if you're not familiar. CCT div is possible at this step. So if the question was find the current flowing through R2, right? Current flowing through R2, you could apply current division and figure it out that way. We did not need to find Vs. That is the point. Does everybody get what I'm saying? We would not need to go all the way up to finding Req and determining Vs as 150. We could simply apply current division if the question was IR1 or IR2, currents for IR1 and IR2. Okay. So depending on the question, you need to understand the statement. You need to look at the circuit diagram, extract as much information as you can from the given information, and then begin your analysis steps or procedure. In this case, I'm trying to cover all different possibilities. Okay. Far so good. Vs is 150. So Vs is 150. That means that the voltage across R1, R2, and R9 is also 150. Right? They're all in parallel. So if you go back here, you can see Vs should be the same up to here and up to here. That's 150 volts applied across the current source, across the 6 kilo ohm resistor, and across the 24 kilo ohm resistor. Vs is also applied to the rest of the circuitry, so I can break it down like this. This was what, R4? No, R3. So R3, R4, R5, and R6. Okay, let's see. 3, 4, 5, 6. Yeah. From the original circuit. From the modified portion. Not even actually modified. We're just looking at the right side of the circuit. Because that 150 volts is applied in parallel, we can consider it to be a voltage source that is being applied to the rest of the circuit on the right. So now at this point, if we want, we can apply voltage division also. Again, depends on what we are analyzing for. So if we wish to apply voltage division, we have a series connection of resistances. We can find the voltage across here because we know R8, right? And we know R9. Right? R9 is basically comprised of all of this. This is R9. Okay. So let's calculate. We can break it up into R3 and R8. R8 is again from R4, R7. R7 is again R5 and R6. So if we want, we can consider this as voltage applied to R3 and R8 in series. Apply voltage division to calculate VR3 and VR8. Everybody remember voltage division? All right, let's solve it. Let's jog your memory. So R3, R4, R5, R6, combine everything, you get R9. R9 can be split into R3 and R8, right? R3 is up top. R8 is comprised of 4, 5, and 6. So I can determine the voltage by applying voltage division across each voltage. And voltage division, VR3 is equal to a fraction of Vs. The fraction is given by R3 to Req of R3 and R8, which is R9. So what is the answer to this calculation? R3 is, what is R3? R3 is 4 kilo ohms and R8 is also 4 kilo ohms. Wait, that doesn't make sense. Hold on. Req, sorry, 8K. It's half. Won't need to do anything. It's 75 volts. All right, so let's go over my work. Do you think it's correct? Or is there an error in there somewhere? You can use Ohm's law and KVL, KCL also to determine these voltages and currents. Do the steps make sense? Let me know if you have any questions. Yes. The question being asked is on quizzes and tests, would the method be provided or stated? And the answer is yes. So that's actually a point of emphasis. And the reason is this. We are accredited, the program that you are enrolled in is accredited by ABET. According to ABET criteria, there is a syllabus, there is a list of topics that we are required to teach students. So if you are required to teach students, we are required to assess a student's understanding and knowledge of those topics. Meaning there could be like 4 different ways to solve the same circuit. But if I have to assess you on KVL, then I will say solve only using KVL. If I teach you voltage division and I need to assess your understanding of voltage division, I will state on the problem, use only voltage division. If you solve it by using Ohm's law and then do not apply the voltage division principle, I have no way assessing your knowledge. So that means you won't get points if you don't show that particular method. Okay. So that's a very good question, very important question, very important answer. Is that clear to everyone? Right? And that's why in that first quiz, I specifically pointed out, not first, the second one, I believe, that we solve only using Ohm's law, KVL, and KCL. Even though we can solve it using other methods by combining resistors, we do not do so because, again, we are required to assess a student's understanding of that topic. And keep this in mind for going forward for all classes. Okay. All right. Do the steps make sense so far? Fully. It might seem convoluted, but again, the purpose is that students should be familiar in applying a variety of techniques to solve the same circuit. All right, so we got 75 volts across each R3 and R9. So if R3 is dropping 75 volts, then R9 has 75 volts. And I can solve this further. by saying this is 75 volts being applied to, how is R9 drawn? R8, sorry. R8 is R4 and R7, so 4, 5, and 6. R4, 5, and 6. And this is R8. We're expanding the circuit step by step. So what do you see at this point? We see there are two parallel branches. That means 75 volts is applied to both branches, R4 and R5, R6, right? That's this node right here, these two nodes. This is plus 75 volts at this point. This is 75 volts at this point. They both combine in series to give us 150 volts across those two nodes. Okay. So 75 volts across that point. 75 volts divided by 20 kilo ohms, I can find IR4 from Ohm's law. 75 volts divided by, what did I say, 20 kilo ohms. Calculate this. And we can also find, now there are two ways to find the current through R5 and R6. Simple as Ohm's law, right? That's a direct pathway. 75 divided by R7. We can also apply voltage division to find the voltage across R5 and R6 because they're again in series. So IR7 would be equal to 75 divided by what is 5K, right? So the answer for this current. And then VR5 is equal to 75 times R5 divided by R7. And VR6, again, from voltage division, is R6 or R7. Anyone have IR4? 75 divided by 20,000. 75 divided by 20K. How much do we have? 3.75 milliamps. All right, see a few nods everywhere. So this is 3.75 milliamp. Oh, sorry. Milliamps. How about the second one? 75 divided by 5,000. 000 milliamps, 5 to 15. 15? Yep. 5 times 15, 75. 75 milliamps, IR7. How about VR5? R7 is, what is R7? 5 kilo ohms. R7 is 5 kilo ohms. R5 is 2 kilo ohms. So 2 divided by 5. What is this answer? And this is 75 into, what do we have? 3 kilo ohms divided by 5K. Yeah, 3. So what's the answer? 150 divided by 5. So that should give me 30. 30 volts. 75 times 3 divided by 5. 5 and 75 is 25 times 3. No, 15 times 3, 45. Is that correct? 45. So if I take 30 volts divided by 2000, I get 15 milliamps, which is IR7. If I take 45 volts divided by 3000, which is R6, again, get 15 milliamps. So multiple ways to solve for the same circuit. There are still a few other quantities we didn't solve for. That is like the currents going through R1, R2, and R3. So we can calculate simply by applying Ohm's law to all of them. Okay. So we used Ohm's law, we used voltage division, we used current division. And there's still a few other places we can apply Ohm's law in there. Let's take a pause. Let me know if you have any questions. I hope the steps made sense. Next problem, we're not gonna go look at all the techniques. Just wanted to show it for this one problem. All good? Okay. All right, series parallel simplification, example 3. Let's take it, let's pick up the pace. So Req from the perspective of the voltage source and I'm going to say this is current Is and this is Vs 120 volts, and then Is is here, I1 and I2 are the resistors current over there. I'm going to call this R1, R2, R3, and R4. Okay. Req, if I start at the far right, I can see 6 is in series with 3, which is in parallel with 18, which would be in series with 4. Actually, you know what? Since I named them, let me use the names. R4 is in series with R2. That combination is in parallel with R3. And that combination is in series with R1. So what is the answer? Req is 3 plus 6, 9. 9 in parallel with 18. Somebody perform that calculation, please. And plus 4 ohms. I keep saying somebody, not somebody, everybody. Everybody perform the calculation. Let me know what Req is. Anyone? 10, 10, 10. All right, great. Thank you. 10 ohms. Does everyone have the same answer? The back, the left, the room? Okay, 10 ohms. All right, so then what is Is? Is would be equal to Vs over Req from Ohm's law. Vs is 120, 120 divided by 10, 12 amps, which is a huge amount of current, by the way. 12 amps is huge. All right, Is is 12 amps. Apply current division. We can find I1 and I2, or we can calculate the voltages across each of those resistors, and we can find Is. So I'm going to write out the steps. You can calculate later. Current division. I1 is equal to Is times REQ divided by R3. REQ in this case is going to be the parallel combination of 18 and 9. Okay, let me explain right here with a simple illustration. Current IS is coming, splits into I1 and splits into I2, right? Did that make sense? So now you can apply current division principle, but REQ is only referring to those two branches. So it's 18 and 9. Okay, 18 and 9. That's REQ. You can calculate that. And I2 is also IS, not also, REQ over, what do we have? R4. So current division, you can find those two currents, I1 and I2. We can also find those values by determining the voltage VR1. Okay, VR1 is R1 times IS, right? So you can calculate that. And then let's say VR3. If you apply KVL, VR3 would be VS minus VR1. Let's take a pause. Make sense? Voltage VS. Let's take 10-second pause. And this would be VR1. This would be VR3. Any questions? Sure. Okay. All right. So VS minus VR1 gives us VR3. So from VR3, I can calculate I1 by Ohm's law, VR3 over R3. And you should obtain the same answer from current division. And then, of course, if VR3 is the same as VR2 plus VR4. So VR2 plus VR4, right? VR3 is VR2 plus VR4 from KVL. I can apply voltage division to find VR2. This would be VR3 times R2 over R2 plus R4. Series combination R2 and R4 form an REQ. And then VR4, you can apply voltage division, or you can take the KVL from the top, meaning this equation. Okay, again, two different ways to find VR4. Apply voltage division again, or you apply KVL, because you know VR3 and you obtain VR2, you can find VR4. That would be KVL. And from there, of course, you can find the current IR, I2. I2 is simply VR3 divided by R2 plus R4. And so you can compare that to the current division answer. Okay. Let's take a pause. You think over that. Let me know if you have any questions. Do the steps make sense? Okay. All right, there's about 4 or 5 minutes left. I'll quickly go over the next next one. All right, series parallel simplification, example number 4. Current source. We want to find Req. Let's call this Is, and this is referred to as voltage V. If I name these as R1, R2, R3, R4, R5, and R6, this is very similar to the, not similar, but the series connections, the parallels are the pretty similar to the first one. So we go to the far right and you pull it and reduce it towards the source. So the far right is we have R4 plus R5 plus R6 in series, which is then in parallel with R3, which is then in series with R2, and that entire combination is in parallel with R1. Okay, on the far right, R4, R5, R6 are in series, then in parallel with R3, in series with R2, in parallel with R1. Okay. And once we have Req, by Ohm's law, V is equal to Is times Req. From there, we can find IR1 and IR2. We expand the circuit one step at a time in the exact reverse order. So V over R1, and then voltage across R2, R3, R4, R6. So let's call this R7. Let's call this R8. And then R9. Okay, R9. So VR9, I can calculate IR9 by current division, and that would be IS times Req divided by R9. That gives me IR9, and IR9 can give me VR2. We're almost out of time, so I'm going to stop in just a few seconds. Okay. So VR2 is IR9 times R2. And so VR8 is VR2. Sorry. VR8 is VR9 minus VR2. Yes. VR8 is total voltage V minus VR2. Once you have VR8, you can find again by applying voltage division and or current division and or Ohm's law to find the voltages and the currents on the far right of the circuit. So there's a class after this. I'm going to stop right here and then go and practice, outside of class, work on this problem, work on the previous problem. Let me know if you have any questions, and we'll pick up here on Friday. Okay. I will post a reading assignment and a homework assignment that will be due most likely like all the way to Sunday. Okay. But it'll be like kind of like two homeworks combined in one. That's why I'm giving like, four Thursday, Friday, Saturday, Sunday, 4 days to do that. All right. So I'll stop right here, pick up here again on Friday.